Most excellent. So friends, today our job is to talk about equilibrium in terms of quiz preparation, test preparation. And all I did was, again, just go in and kind of grab a few sample problems from quizzes that have been taken so far, kind of giving a look to each of the objectives. And so just for no other reason than I went in order, you're going to start kind of seeing the equilibrium problems start what I would say somewhat easier and then build into more complex ones. So to start with, really just considering the term, the equilibrium expression or an equilibrium constant. One of the first questions I pulled from a practice quiz was writing out an expression itself. So here I'm given an example of a reaction where I see I have got a gaseous hydrogen reacting with solid iodine, and it's forming two molecules of gaseous HI. And we're just simply asked to write out the equilibrium expression. So I picked this one on purpose just to remind ourselves that pure solids and pure liquids drop out of the equilibrium expression. And one of the most common mistakes is, especially if we're rushing, which sometimes we do on a quiz, you just kind of get that testing anxiety going, adrenaline starts to pump, whatever it might be, and you make simple mistakes. But I'm reminding us that the pure solid does not become part of that equilibrium expression. And so this one would simply be taking the product, which would be the concentration of HI, and we know that the power with which we raise would be squared based on the coefficient. And then we simply set that over the concentration of molecular hydrogen, and it's to the first order since its coefficient is 1, and we don't talk at all about the solid iodine. So that was a nice simple warm-up, just a friendly reminder that if you're given an equilibrium, we call this a heterogeneous equilibrium. Just simply meaning that we have different phases of matter. We have gases and solids. Another way to remind yourself is only include if you see gases or if you see aqueous. Those are the adjectives that you would say, okay, those are the ones that must be included, and solids and liquids would drop out of that expression. Okay, so a good warm-up. I then placed this example in as kind of a way to apply what we just practiced. I'm going to write this equation with you. We have solid carbon combining with gaseous carbon dioxide in dynamic equilibrium, and I have two molecules of gaseous carbon monoxide. Okay, and it says at a certain temperature, 1273 Kelvin, the Kp is given to us as 167.5. What is the partial pressure of carbon monoxide at equilibrium if the partial pressure of carbon monoxide, if the pressure of CO2 is 0.17 at this temperature? So one of the first things we do is make sure we're comfortable writing out what the Kp expression would be, realizing that this solid carbon is not part of the overall expression and therefore wasn't even mentioned in terms of quantity. I mean, it makes no sense to talk about a pressure for a pure solid, right? So that's why it doesn't even get mentioned. But sometimes I think that's upsetting to students because not every ingredient is mentioned, but we don't need the solid. So the Kp would be the partial pressure of the CO squared due to coefficient set over the partial pressure of carbon dioxide, and its coefficient is a 1. And since these are all equilibrium values, this is always the exciting part when you read a story problem and it actually says you're at equilibrium and you go, yes, I don't need an ice chart. And that's kind of one of the first word clues, is that you don't need an ice chart if you're given equilibrium values. So this problem really is straightforward. We have Kp equal to 167.5. We're looking for CO, so I'll just let that be X, but X is going to be squared. There's the partial pressure of CO set over the equilibrium concentration of 0.17 for CO2. And we just solve for X and find the carbon monoxide pressure. So we would just take 167.5 times 0.17 to get X squared, and then of course square root that answer. And if I could have just a quick moment, I'd like to hit that just to make sure we have a common answer given. 167.5 times 0.17, and then square root that answer. And I get 5.33, but about 5.34 atmospheres. Let me pause a moment and see if there's any question as you're processing what made this question easy or hard. If you saw this one on your quiz, would you think easy or hard? I square rooted the product of 167.5 and 17. Let me just back that out. 167.5 times 17, square root that product, and you get X. This is equal to X squared. Let's see if I hit that. It was 28.75 on your calculator, and that would have been X squared. So that's where I pulled out X. Other questions or comments? No, pure solids or pure liquids are not part of the equilibrium calculations. They're not part of the expressions. They simply drop out. Good question. Don't confuse the liquid phase as the same as the aqueous phase, because those are not equivalent. Pure liquids, pure solids, these are no, but aqueous and gases are a yes. So those are the phases of matter that you look for when you're writing out your expression. Correct. Cool. Got it. Excellent. All right, let's keep moving along. Reaction, again, I'm going to just write it with you. I like to have workspace. I have gaseous hydrogen reacting with some gaseous chlorine, setting up an equilibrium with two HCl's, all in the gaseous phase, and it gives me a Kc value of 1.22 times 10 to the 33rd power. That is a magnificently large number. So I can tell that the equilibrium is definitely favoring the forward reaction, right? That's a huge number. It's asking us to convert from Kc to Kp. So we're looking at a balanced equation converting a Kc to Kp, and this is one of those equations that we should know, that Kp is set equal to Kc, and we take the ideal gas constant R times the Kelvin temperature and raise that to the delta N. That's our formula for converting Kps into Kcs or vice versa. Remember that delta N is defined as the gaseous products minus reactants in the gaseous phase only, because Kp specifically for pressures of gases. There's ideal gas constant, and since typically our pressures are given to us in atmospheres, we'll use 0.0821. We were given a Kelvin temperature of 301. 301 Kelvin. And the Kc again was 1.22 times 10 to the 33rd power. We're asked to solve for Kp. Well, what made this question unique or upsetting, I suppose, is that delta N, the change in gaseous moles of product, minus gaseous moles of reactant, which we could see there's 1 mole of hydrogen plus 1 mole of chlorine, is also 2. We take 2 minus 2, we get a 0. So what that means is that there's exactly the same number of gaseous moles of products as compared to the gaseous moles of reactants. So this delta N is 0. So what that means is, if this makes sense, any number raised to the 0 power just write that down, is equal to 1. I mean, just check that on your calculator. You can take a random number. I'll press the number 5. Raise it to the 0 order and your screen will read 1. So 0.0821 times 301 Kelvin raised to the 0 order is just the number 1. So what happens uniquely here is Kp is exactly the same number as Kc when the delta N equals 0. And I think sometimes the easiest problems get us upset when we're quizzing and go, oh, there's got to be a trick to this. It can't be the same number. But here is exactly the same number. Kp would come out to be this extraordinary large 1.22 times 10 to the 33rd power, which is what Kc was given to us as. Let me give you a minute to think through and see if a question pops up. The 0821 is the RT value every time or just in this problem? Every time. So let's say, for example, I have a gaseous mole of A plus a gaseous mole of B plus a gaseous mole of C, and I just say, oh, it's going to make a gaseous mole of D. See how random I'm being? And I'll make Kc equal to 20. So this is a totally made up problem, but it allows me to kind of emphasize the math. What if they're not the same number? Let's say that the Kelvin temperature has to be given in the story problem as well, and we'll say it's 1,000 Kelvin units. Find Kp. So very similar to the problem above. I just made up a problem instead now where we have a different number of gaseous moles of reactants compared to products. So my Kp will be found by taking Kc and then going RT delta N. That's our formula. The delta N here, since it's just 1 gaseous mole of product, but there's 3 combined gaseous moles of reactant, 1 minus 3 is now -2. So to solve this problem, the Kc, which I just made up as 20, times 0.0821, and the temperature I just randomly made is 1,000. This now gets raised to the -2 power. So the R and the T are placed in there's, the R is a constant, but the temperature could change as you're reading the story problem. And I would say 0.0821 times 1,000. And when I do that, I get, that came out to be 82.1, and that's still raised to the -2 power. Just that So 82.1 raised to the negative 2. I hit that on my calculator. I get 1.48 times 10 to the negative 4. And finally, I can take that and go times 20. And my new answer is 0.00297, which would be the KP, a very different number than the original KC given to me. So the 0.81 is constant. The temperature varies by the problem, and that product is raised to the delta n. That strategy is employed each time we're converting KC to KP or vice versa. Let me give you a moment to think about that. Oh, sweet, you're welcome. Go back to the second slide, you bet. Any comment here? All right, let's see if I can find, well, here's one. Again, this is a thought question. It's non-computational. So it's just kind of asking us to think about the term the equilibrium constant and what makes the constant a constant. Well, we know that the equilibrium constant is dependent on temperature, that an endo or an exothermic reaction for Le Chatelier actually changes the value of the K constant. So I want to emphasize that Ks are dependent on temperature. And you will get a new established number for an equilibrium constant if you warm or if you cool a reaction, depending if it's exo or endothermic. The next choice says the nature of reactants and products. And I wanted to explain that that's actually a true statement as well, focusing back on, remember that we do not include solids or liquids in the equilibrium expression, but we only include aqueous and gases. So when it says the nature of the reactants and products, that's truly what it's going after, the phase of matter. So it is dependent on not including solids and not including liquids and only including the other two phases. So number 2 is also a true statement. And then 3 and 4 says the concentration of reactants or products. And based on Le Chatelier's principle, we would know that I can upset an equilibrium by changing the concentrations, but it will reestablish the same number by pushing forward or pushing in the reverse direction. So Ks will not change based on concentrations, but they will change by temperature, and they're not including solids or liquids. So again, I included this one because sometimes the term nature of reactants and products, sometimes it's been unclear what that vocabulary word was going after. So I wanted to just kind of expand on that. Give you a moment to think. Any comments for the chat? Thumbs good with this one? Here's a question. Oh, it looks rather long. So let's take it slow. Nitric oxide is formed. So, okay, this is all nice to know stuff. An important pollutant in air formed from its elements, blah, blah, blah. Here's something interesting, the reaction. So I'm going to just write with you N2 plus O2 is in dynamic equilibrium with 2 NOs. And the equilibrium constant is given to me as 0.01. So again, part of being a good quiz taker is to skim through that information that's nice to know and get to the reaction, right? So my eyes kind of went through this rather fast, and right here, this looked important. Predict the direction in which the equilibrium will move to reach equilibrium at the same temperature if I place 0.4 moles of nitrogen in with 0.1 moles of oxygen and 0.08 moles of the NO. And this is all in a 1 liter container, so those are already molar units. So that's the moles per liter unit. So what's interesting here is we're given these molarities of reactants and products and asked which direction is this heading? Is it at equilibrium? Is it not yet there? What's happening? And this is the opportunity to remind us of a term called the reactant quotient and compare it to the known equilibrium constant. So the strategy here, since we're given all of the information about quantities of all reactants, all products, let's calculate where we're at so far. Calculate Q, the reaction quotient. We know it's done exactly the same way as calculating an equilibrium expression. So I'm going to calculate using the concentration of NO squared over the concentration of N2 times the concentration of O2. And I'm going to compare the reaction quotient, the number I get, to the established K of 0.01. And those two numbers, when compared, will let us know what direction it's heading to achieve equilibrium. So we have NO given to us as 0.08. That needs to be squared. Set over the nitrogens 0.4 and the oxygens 0.1. Let me hit that quickly. 0.08 squared, whoops, divide by 0.4 and 0.1. My screen reads 0.16 on my calculators. Anyone else get that? Yes, awesome. So here's what we've determined. Q has come out bigger than K, right? 0.16 is a larger number than the K. So that's great information about telling us what do we need to do to that number to get it smaller, right? Q is too big. If Q is too big, what direction is going to make it go into a smaller number? Well, it's going to be to make the concentration of the product smaller, and we want the concentrations of the reactants to get larger so that quotient becomes a smaller number. To consume the product and make more reactant, we know that the equilibrium has to be shifting to the left. So when Q is too big, you know it will shift left. We've learned also that if Q is too small, you need to make more product, and so it will shift to the product or shift right. And the last condition we learned was that if Q is exactly equal to K, then you're at equilibrium. So that problem, I got to go through an example where you would employ Q, the reaction quotient, calculated exactly the same way as a K constant when we get a number. And that number is used to compare the magnitude versus the known K to decide what direction that the equilibrium is heading. What might be a question on this problem if you were to face it down on test day? Anything for the chat to share? Tell me in the chat, are you confident of calculating Qs? Nothing? So with that, that's okay. Better. Oh, perfect. Thank you, Heather. I'm only assuming that if I don't see something come up in the chat, we're good to go on, which is totally fine, but please don't hesitate in slowing me down or asking a question. And I'll just keep moving to show several examples as long as we have time to work together. We have a question, and as I kind of go through, I'll write this equation with you to kind of help you write down. We have 2 units of NOBR in gaseous phase in dynamic equilibrium with 2 NOs and BR2. I say the keyword initially, because when that's a keyword for me, it talks about, oh, I'm going to have an initial, a change, and an equilibrium. Just by seeing that keyword, it's initially filled with pure NOBR. And it's filled with 4 atmospheres of pressure. The other keyword I see as I'm reading through is after equilibrium was established, the partial pressure of NOBR was now 3.1 atmospheres. Seeing the equilibrium lets me know to fill out the bottom row, the E. Calculate the Kp for our reaction. Well, I know Kp will be found by taking the partial pressure of NO2 at equilibrium squared times the partial pressure of bromine, all set over the partial pressure of NOBR, also squared. We've got a little bit of work to do in our ice chart to figure out the equilibrium values of each ingredient. So one of the things that's interesting as we get better and better at ice chart, I see students very quickly know that those are zeros. As the reaction begins, initially starts, there are no products made. So I know I can fill in those 2 boxes with zeros. There's one more box that I can fill in, and that's how much this part changed. Because I can subtract 4 minus 3.1 and figure out that that decreased by a factor of 0.9 atmospheres. So I'm going to make sure I say, okay, it's decreasing by 0.9 ATMs. Having the initial and the equilibrium lets me figure out the change. And now that we have the change figured out, we use stoichiometry to calculate the other 2 change rows, right? This is stoichiometry dependent. So in other words, if I start with 0.9 atmospheres of NOBR, and I'm just showing some stoichiometry, we see that there's 2 moles of NO made for every 2 moles of NOBR consumed. So that's the same number. It's a 1 to 1 or a 2 to 2. It's the same number. So if this decreases by 0.9, this is going to increase by 0.9 because the coefficients are the same. But with bromine, remember that we have a little different ratio. If I start with 0.9 NOBRs, and I see that for every 1 mole of bromine formed, it would consume 2 moles of the NOBR. Now, this is not anything you have to write down. It can be mental math, but I'm just trying to show, that second row, the change row, is all stoichiometry, mole problems. 1/2 of 0.9 is 0.45. So this is going to increase by 0.45 atmospheres. So I use stoichiometry to finish the rest of the row for change. And now I have what I need. This is 0.9, this is 0.45, at equilibrium. So once I've determined that, it's just a matter of plug and chug back up here into our Kp expression. So Kp would become the concentration of NO2 squared, or the pressure, times 0.45, and that's all set over the 3.1 squared. With this example, we were given an initial in the equilibrium that find the change of that initial reactant. Did a little mole work with stoichiometry to figure out the rest of that same row, and then we're ready to plug in for the final answer of Kp. When I hit that 0.9 squared times 0.45 over 0.1 squared, screen saying 0.0379 is probably too many sig figs, but somewhere close to 0.0438, somewhere in there. What might be challenging if you're looking at this problem of how to start? What might be a tripping point? Any comments to share before we look at another one? Any comments? All right, I'm going to try to go through and find a different example. I'm going to skip ahead a little bit. Let's try, not that this is challenging, I'm just trying to find something that's a little different. So here's a question, I'll write with you. It says we have an equilibrium between two NO2s, two NOs, and O2. Consider the following equilibrium system. Kp is given to me as 0.738. Find the equilibrium pressure of oxygen if the NO2 gas pressure is 0.52. The pressure of NO is 0.3. And here are those just words that we love to read. At equilibrium lets me know I don't need an ice chart because these are equilibrium values. So this story problem really is just asking us to solve for X. And we have all the information provided for us. And sometimes I always think it's the easiest problems that get us. We know that Kp is equal to the partial pressure of NO, but it would be squared, times the partial pressure of oxygen. Oops, that's too big. All over the partial pressure of NO2 squared. This is the target variable, and we have everything else provided for us. So just simple algebra will help us find 0.3 squared. I'll let oxygen just be X and set over 0.52 squared. Point 738 times 0.52 squared divided by 0.3 squared. Let me just give you a moment to see if that answer matches anything on your screen as you hit for X. Thank you. Okay. So again, pretty straightforward, just looking for an opportunity to try the easy ones. And if you're ready, how about something where we need quadratic equation? Let's move to this question, try to up the math a little bit. I'm going to write this reaction out with you. It says we have some hydrogen. Oops, what was the last answer? So sorry, Joe. Backing up 0.1. Cool. All right, that's good. And I just went to a next screen. Here it is. We're going to look at a reaction in which hydrogen and iodine react to make two HIs. The K is given to me as 49.5. An equimolar mixture of reactants give the concentration of the product at equilibrium to be 0.5 molar. Determine the equilibrium concentration of the hydrogen. So ultimately, we'd like to know X, the initial concentration of hydrogen. Determine the equilibrium concentration. So I'm going to let these equimolar concentrations of iodine and hydrogen just be X. The other thing I know is that initially I have no HI. What can I figure out first based on the knowledge that HI initially is 0 and equilibrium, it's 0.5? Well, what I can determine there is the concentration increased by 0.5 molar. I can determine this just by subtracting. If I started with 0 and ended with 0.5, it changed by 0.5 molar. And what else I can do is figure out the change based on stoichiometry for the H2 and the I2. So if HI was made as 0.5, just thinking about stoichiometry, we know that 1 mole of hydrogen is needed to produce every 2 moles of HI. So I'm just doing that 1 over given ratio. 1/2 of 0.5 is 0.25. So what does that mean? It means that X decreased by 0.25 moles. Well, I can do this. Change that here. Sorry, this is X went down by 0.25 moles. I can see that both of those are going to decrease with a 1/2 stoichiometric ratio of how much the HI increased. So this is the row for equilibrium. We have X minus 0.25 being the equilibrium value of hydrogen, as well as the equilibrium row for iodine, and we have HI now as the 0.5. We know that 49.5 would be equal to the concentration of HI squared set over reactants at X minus 0.25 respectively. So just to backtrack, kind of going through the problem, we were given the initial as 0, the equilibrium as 0.5 to determine the change in the product. Based on the change in the product, we use stoichiometry to find the change row in terms of the reactants, and use that variable then to solve for the equilibrium, knowing that ultimately we want to know the concentration here of H2 and I2. So let's FOIL. We have x squared minus 0.25x minus 0.25x, and then it becomes plus 0.25 times 0.25. So when I take minus 0.25 minus 0.25, you can see how that's just x squared minus 0.5x plus 0.0625. That's simplifying. And again, I know we all have, coming in with different algebra strengths. So I'm just kind of going through very slowly the steps of distributing first, outer, inner, last, and simplifying x minus 0.25 multiplied there. To continue that math, what we still have here is 49.5 now needs to be distributed through that. And that's still equal to 0.5 squared, which I simplify as well as 0.25. And you can see now that it's going to be a quadratic equation formula, right? We have some x squared, some x, and the a, the b, the c of the quadratic formula. Let me distribute. We have 49.5 x squared minus, so 49.5 times 0.5, 24.75x plus 49.5 times 0.0625. Now, ultimately, we want to have this set to 0 so that we can solve using the quadratic formula. So I'm going to subtract 0.25 from the number that has no variable with it. So when I hit 3.09375 minus 0.25, my answer here is 2.84375 is now equal to 0. And now what we have is a quadratic equation formula, and I've encouraged you to consider putting that right onto your calculator just as a program so that it makes solving so much easier. And we'll come up with 2 answers for x. You'll know one of them will be a nonsense answer and the other one will be correct. So let me hit that on I have a program for quad. And so I simply put in the letter A as 49.5, the letter B as negative 24.75, and the letter C is 2.84375. There are 2 answers. One of them reads 0.1789 with more decimals, or 0.0068. Those are the 2 possible choices on my calculator right now. Which one of those would make no sense? So this, as you come back up here, we have to be able to subtract 0.25 from this original answer, right? And so if x, so just to kind of think about what this is saying, 0.1789 or 0.0068, that's kind of where you're at in terms of finding that correct answer. And you have to be able to subtract that. So when you looked at this multiple choice question, it asked you to solve for x, and it came out to be the smaller of the 2 answers, knowing that you had to subtract a smaller number. How do you feel about the quadratic equation and you start solving through here? Are you able to process and pull out an X? Do you have a program on your calculator? Any questions about how to solve there? If I could be of help with the algebra at all? I hit the button. What did I plug in to get those last two numbers? The last two numbers I hit, let me my screen. Listed right here in my quadratic equation formula. So the number associated with x squared is called an a. The number associated with x is called b, and the number that has no variable associated is with a c. And the question is, do you always pick the smaller x? The answer to that is typically, to be sure that I can think of an example where I wouldn't. Typically, when you solve for x, one of them will be a negative number and one of them will be a positive number. Always pick the smaller. If they both come out positive, you want to pick the smaller of those two values, knowing that you're having to subtract from that original quantity. So yeah, that's always a good way to think of it. Good processing there. The vast majority of the time, this is what I run into. The nonsense number is always negative because there's no such thing as negative pressure or negative molarity. So that's an easy one to decide. Let me re-hit that then. If Ryan, you say you got different answers, I'm going to hit quadratic equation again. A went in as positive 49.5. B went in as negative 24.75. And C went in as 2.843. I'm getting the same thing on my calculator again. 0.178 and 0.0068. Double check. Anyone else? So have you in terms of matching Ryan or matching mine? Oh, matching Ryan's. So this, interesting. I'm going to wait. So let's verify, because that's really important. If you two are getting the same answer, I have a second calculator. Yeah, sometimes my function got a different answer. I don't know why. So let me work on that and see if my quad formula and my calculator is giving me a different answer. But the two of you verified yours, so that's interesting. Which makes me think if you two match, that's probably on my end with program. I got the same as Ryan and Heather. Well, let's toss me out then. Which actually, the number itself, if you think about the value of x, the number itself has to be large enough to subtract out 0.25, thinking about the math. And the answers that you're sharing actually make better sense, don't they? Because your second number that you wrote is a large enough number to actually subtract out the 0.25 and have the molarity there. Yeah, so thank you, Ryan and Heather, and weird from Ryan that, yeah, Ariana, same. So that's third motion. So going back to check that with my, I know, right? My program. So I have two calculators. I'm going to try them against each other, but I won't waste your time doing it right now. We've got 3 people agreeing that the final answer was different than my program was giving me, so I'm relying on you.
So, quick question then, would the values that we pick then, for which one's the right one, it would be 0.321?
So, you know, interesting is, go back to the question and be careful, reader. Determine the equilibrium concentration. So you're almost to the right answer, right? Because at that 0.321, 0.321 minus 0.25 would actually be the multiple choice answer you'd have to select. So 0.321 minus 0.25. Yeah, and I have to reprogram my calculator, but thank you for letting me find that before I go on and record more videos. 0.071 is the equilibrium because I have to take x minus 0.25. That's what I would want circled for my final answer. But it also brings up a very valid point of why the other one doesn't make sense, right? The first one I circled was too small. This 0.178, I couldn't possibly take 0.178 and subtract the 0.25. That's a negative number. So that's how I know to toss that one out and pick the number that was large enough to find the equilibrium concentration. Time like that. What do you think?
So without the program, how would you plug it in?
Without the program, you spend so much time solving. So you'd have to go through and use the quadratic formula. Do you know that by heart? There's a little Pop Goes the Weasel song.
Like, does a
Here it
TI-30,
is.
would that work? Does that have the program? I just don't know.
A TI-30? No, I don't think you can program that. You'd have to sit and plug this out. But I'll tell you what, on when you open your quiz on the respondus menu, there's a scientific calculator there. If you don't have a TI calculator, like I'm going to say an 83 or above that you can program, I don't think that would have a program there either. If you don't have a way to program without a scientific calculator that's like an 83 or above, you have to take that and actually solve the math. And that's why I encouraged you, if you had access to the scientific calculator, to just create your own program where you could see on the screen, I was just entering A, the B, the C, and then hit enter, and bam, you get your answer that way. That this is terrible, it's just time consuming.
Yeah. Well, I think my roommate has a calculator for me, so that works out.
There you go. And in the feedback of your notes, when you submitted them, I included a YouTube link of how to program that in, but you could really Google that fast, and YouTube will give you videos of how to program it in. It might already be on your calculator, but if it's not, create a program, and you just save so much time doing algebra, you know. That's, I don't want to say that it's not important, but to me, I just want the answer. I don't want to do the algebra. Yeah, for sure. Cool. Shall we try another one? We have a few minutes left. Let's see. This one looks really tiny, but it actually, let's see if I can, yeah, let's do this one only because it gives me a little bit of an opportunity to talk about solids and how they play a role again. Let me write this with you. We have a decomposition of calcium carbonate in a solid form in dynamic equilibrium as it decomposes with calcium oxide and carbon dioxide gas. Alrighty.
There you go.
And the Kp is equal as 1.16 at 800 degrees Celsius. I'm going to place in 47.6 grams of calcium carbonate, and I put it into a 10-liter container. It's heated to 800 Celsius, and it's asking me what percent of the calcium carbonate reacted to reach equilibrium. Now this one I selected because it brings us back all kinds of review with the ideal gas equation, our good old friend PV equals NERT. And let's kind of process what information we're given. I have a dynamic equilibrium and a Kp value. Well, I know that Kp, just in terms of its expression, is related to products over reactants, but only for things that are in the gaseous phase. So it's equal to the partial pressure of carbon dioxide, and that's it, isn't it? There's no other pressure for gases to consider. So what's interesting with this problem, it gave me the partial pressure of carbon dioxide by telling me the Kp. Since 1.16 is the partial pressure of carbon dioxide, we know the partial pressure, 1.16 atms. So that was the kind of the trick with this question, is realizing since there's just one gas, it's only affecting the Kp. It's giving me the pressure of carbon dioxide at these conditions. What we can use is called the ideal gas law, PV equals NERT, and solve for the moles of carbon dioxide present, and then do a little stoichiometry to find out how much calcium carbonate was consumed to create that pressure. So the pressure was given to us as 1.16 atmospheres. The volume was given as 10 liters. I know moles of carbon dioxide, that's N. R is our gas constant. And temperature will have to be in a Kelvin unit, so we'll be sure to convert 800 plus 273. And when I solve for N, that's going to be moles of CO2. A good old PV problem. 1.16 times 10 divided by R and T. My 13, now I'll round a little bit, 1317 moles of carbon dioxide. Back to your equation, if I know this number of moles, I use stoichiometry to convert over to this number of moles and then find its mass. So for 0.1317 moles of carbon dioxide produced, I required the same number of moles of calcium carbonate, and I can convert that to a gram by using its molar mass. 40, 48, and 12. This is 100. So that answer times 100. Oops, that didn't come out very neat. If we started with 47.6 grams, whoops. We use 13.7 grams, they're asking us what percent did we consume. So this allowed a ton of review in terms of I had to use stoichiometry, I had to use the gas law, I had to apply equilibrium as well. Let me give you a minute to think this through. I'm going to scroll up so you can see the original question, right? We were given a mass of calcium carbonate. We wanted to know what percent of the mass reacted. So our process of using Kp for the partial pressure of carbon dioxide, turning that into the mole unit using the ideal gas law, finding mass using stoichiometry, converting it out to a percent consumed. Maybe a moment to think about this one. See if you have a question, jot it into the chat. I have so many more examples that we want to go over, but I'm going to save some of these for Saturday's review session as well. I'll be back here, I think, Saturday at 10 a.m. And if you can't make it, I will record that. Ariana says I got 27.7 for the percent. Final answer. Oh, you know why? Because this is a 17. And I put it in as 7. Cool. Yeah, I think I found my mistake. This answer here, I transposed it incorrectly up here. Instead of having 0.17, I had just written 7, but it should be 0.17 there. And you'll get that common answer. It's nice having a calculator buddy, isn't it? Cool. Good, that's awesome. 27.7 when we solved KPs with ideal gas law and using some stoichiometry, we reached that answer. Same, sweet. So I'm going to ask a favor. I'm going to just stop the recording for now. That was our review session. But if you have a topic that you'd like me to include by Saturday's review session, if you wouldn't